all of that to the 3/2. Oh, actually, it's to the power, it's cubed now, not to the 3/2, because we've squared it, because we have a rho squared term here, and there's a dr over here. We're going to non-dimensionalize this integral. We'll let x be equal to r over rc, and then the integral becomes, we'll just call it I, and it's equal to 4 pi times the integral of x squared, there are 2 powers of r upstairs, dx over, so this is the non-dimensional part, 1 plus x squared quantity cubed, and we can do this, we can let x be equal to tan theta. This cries out for trig substitutions. It's 1 plus x squared. If we make this a tan theta, we get a 1 plus tan squared theta. It's a secant squared theta, secant cubed. You plug in these things, differential. And what you discover is that this integral I is equal to pi squared over 4. What are these? Of order unity things. We take our luminosity here, and our luminosity is given by whatever our integral was I, which is pi squared over 4, rho g0 squared, we've taken it outside the integral, mp squared, mass of a proton downstairs, lambda prime, our emissivity coefficient down in front there, T8 to the 1/2, that's going to be more unity, and we had 3 powers of radius over here that we've integrated over 4 pi r squared dr, so there's an rc cubed over here. We can solve this for rho g0 squared, and we get rho g0 squared is equal to the total luminosity, the mass of a proton squared, over our lambda prime times T8 to the 1/2 I, our integral, which is pi squared over 4, rc cubed. So here we have rho g0 squared, the density of gas at the center required to produce the emissivity. Here we have rho d0 squared, the dark matter required to produce the velocity dispersion that we see in the cluster. We can take this quantity and square it, and take the ratio, rho g0 squared over rho d0 squared, and ask, is the gas density sufficient to produce the dark matter, to produce the gravity which we're attributing to dark matter? We get over here 2 times L times mp squared, gravity squared, rc over T8 to the 1/2 I sigma to the 4th, because we had to square the dark density, times lambda prime over here, and then we can plug in some numbers. What numbers do we plug in? Oh, the luminosity of such a cluster. It's huge. Actually, that's the temperature. The luminosity of the cluster is on the order of 5 times 10 to the 44 ergs per second. Remember that the sun is 2 times 10 to the 33 ergs per second. So this is 10 to the 11, more than 10 to the 11 solar luminosities of X-ray coming out from the cluster, from Bremsstrahlung, not from photospheres. The velocity dispersion will take to be 1,000 kilometers per second. I should write more clearly because this is being recorded for posterity. The temperature is the X-ray luminosity, X over here for X-ray. The temperature is 10 to the 8 Kelvin. Give or take a few. Core radius on the order of 0.2 megaparsecs. Mass of a proton, 1.67 times 10 to the minus 24 grams on most days. And Newton's constant, which is better in this case to use conventional units, 6.6742 times 10 to the minus 8 centimeters per second squared, centimeters per gram. And when we plug in all these numbers, can the gas be the thing that's producing the velocity dispersion? Is the gas the thing that's producing the gravity? And the answer is no. And you can push the numbers, and people push the numbers, and the answer is there's just too little gas to produce the dark matter. Now, then you could say, is it neutral gas? Is it gas that's warm gas at 10 to the 4 degrees Kelvin? That'll have emission lines. You don't see the emission lines. You don't see the neutral gas emission lines at 21 centimeters. You don't see the molecular lines. If it were molecular gas, H2, you don't see carbon monoxide emission. It's not in any form that we can find, which is one reason we hypothesize that it might be in the form of bowling balls, or it might be in some form that's non-baryonic, as we now think. The fact that you can't say what it is doesn't mean that it must be something else. It must be, you just know what it's not here. But it's not gas, and so the excitement about whether or not X-ray emitted gas was the source of the dark matter died down. X-ray gas is still a wonderful way to study clusters of galaxies. There is more mass in the X-ray emitting gas than there is in the stars in these galaxies, in these clusters of galaxies. And it's spread fairly uniformly, with this roughly isothermal sphere distribution maybe falling off a little bit more rapidly than that. Let me say a few more things about clusters of galaxies before moving on to our next subject. I've already said the typical radius of a cluster, of a big cluster, might be on the order of 1 megaparsec. The distance from us to M31 Andromeda is 0.7 megaparsecs, so that's the scale of a megaparsec or two. You can ask, what is the crossing time for a cluster? And the crossing time is the size of the cluster divided by the velocity dispersion, which is 1,000 kilometers per second. So here's a wonderful fact for those of you who are going on in astronomy to remember. A kilometer per second is a parsec in a million years. Almost exactly. So this turns out to be 10 to the 9 years. So you don't get, the galaxies don't get to cross the cluster a whole lot. It's sort of 10 cluster years if they were in circular orbits. And in circular orbits, they wouldn't even go around that many times. So the clusters are dynamically young objects. They haven't been around for many dynamical crossing times. Interesting objects in that regard. What else do I want you to know about clusters of galaxies? We see very little star formation in clusters of galaxies. In clusters of galaxies, we see high bulge to disk ratios, typical of SB and SA galaxies. A lot of elliptical galaxies. Very few galaxies that are forming stars. We think what's happened is that as these galaxies go through the cluster of galaxies, the hot gas that we were seeing the X-ray emission from strips out the cold gas from these galaxies, and the cold gas heats up and joins the hot gas. So the cold gas has been lost, and they no longer have cold gas to make stars. There are exceptions to this, but they're few. So the galaxies in clusters of galaxies, at least today, at redshift 0, look to be old and rare, hot too, although more metal-rich. Now, if you don't like this argument about it's not being gas, there is another way to reach the same conclusion. Instead of measuring the velocity dispersions of the galaxies in the cluster to measure its gravity, you can measure the gravitational lensing produced by the clusters of galaxies. We'll talk about gravitational lensing. I meant to say this. We'll talk about gravitational lensing on May 17th, which was to have been a study day for finals, but since class on April 24th was canceled, we will be meeting on Friday, May 17th. The chair of the faculty has said that that we're allowed to have one extra class, and we will. So you can use gravitational lensing to determine the density of dark matter. And to determine the density of the gaseous matter, you can use something called the Sunyaev-Zeldovich effect. The way the Sunyaev-Zeldovich effect works is that there is something called the microwave background that we'll talk about. The cluster of galaxies has hot gas in it. That hot gas inverse Compton scatters the microwave background. And so wherever there was a cluster of galaxies, you see a change in the microwave background due to the scattering by that hot gas. It's an interesting, and I'll explain what the signature of that is. But so you can determine the gas constant from this in the Ives-Aldovich effect. You can determine the dark matter density from gravitational lensing. And again, the gas in clusters of galaxies is 15% or 20% of the total mass, and that's it. And the stars are much less. So the baryons that we can see don't contribute. Okay, I have 5 minutes left. We will start the subject of cosmology, and this is actually a very auspicious day. Since, for you at least, it's April 26th. 93 years ago, there was, to the date, there was a debate in Washington between Harlow Shapley, who was at that time at the Carnegie Observatories, but went on to be the director of the Harvard College Observatory, and Heber D. Curtis, who was at the Lick Observatory, and a distinguished observer. There was a debate between the two of them, which was entitled "The Size of the Milky Way." And this was the pressing issue of the day, and the reason that it was the pressing issue of the day is that it was thought that the Milky Way was basically the whole universe. That there was the Milky Way galaxy, it had stars, and that was it. Well, not quite. Heber D. Curtis thought that the Milky Way was relatively small, in which case he argued that the spiral nebulae couldn't possibly be within the Milky Way, and instead had to be Milky Ways in their own right, factors of 50 and 100 times more distant than anything within the Milky Way. On the other hand, Harlow Shapley was arguing for a very much bigger Milky Way, not a factor of 3 at least bigger Milky Way, and he argued for a variety of reasons that the spiral nebulae were within the Milky Way rather than beyond the Milky Way, and for a bigger Milky Way. Now, you know what the truth is, but by all accounts, Shapley won the debate, not Curtis. And if you go back and read the arguments that the two of them made, you will find Shapley's arguments more persuasive than Curtis's arguments, even though Curtis was right. Now, it turns out some of the observational data on the basis of which Shapley was arguing was mistaken, was wrong. But they were making the best argument they could at the time, and Shapley was more persuasive. This returns to what I said last time, which is that it is not enough to be right. You must also be persuasive. Indeed, if you're not persuasive, then you might as well not have done the work. So it's important to be persuasive. Okay, so a couple years after that, Edwin Hubble goes out and he measures Cepheid variables in Andromeda, and suddenly Andromeda is 50 times further than Shapley said it was. It's clearly a Milky Way in its own right. Moreover, the other spiral nebulae, which are smaller than Andromeda, but look just like it, must be even further away and fainter. And so suddenly the universe is bigger by a factor of on order 100,000. So Hubble expands, increases the size of the universe by a factor of 100,000. 3 years after that, Hubble makes another discovery, working with data obtained by a man named Vesto Slipher. Slipher worked very hard to make a spectrometer that could measure the Doppler shifts of spiral nebulae. It's hard because they're fuzzy, and so you need a different, and they're low surface brightness, so you need a different kind of spectrometer to measure their Doppler shifts than you need for stars. Slipher made such a thing. He accumulated the data over many long, cold nights, and he found, to his surprise, that most of the galaxies he saw were shifted to the red, which means moving away from us. What Hubble did was measure distances to galaxies, and when Hubble plotted, and I believe he plotted velocities over here and distances over here, he found a linear relation with the velocity proportional to the distance. The constant out in front, he didn't call it the Hubble constant, but we do. And today it's known with reasonably high accuracy. It's 70 kilometers per second per megaparsecs in funky units. Now, since a kilometer is a distance unit and a megaparsec is a distance unit, you can take this number and make an inverse time out of it, and 1 over the Hubble constant is approximately 13 years, 13 billion years. The galaxies are behaving as if at some early time there was an explosion, and since that time, and they all acquired different velocities at that time, and since that time they've all been moving away from the center of that explosion, and the faster they were moving, the further away from the center of the explosion they've gotten. And it looks as though that explosion, if you want to call it an explosion, was 13 billion years ago. So Hubble first discovers that the universe is very much bigger, and second, he discovers that it's expanding and that there is a beginning to time. There is something peculiar about this, and something that's peculiar is that it makes it seem as though we're at the center of the universe. Everything's receding away from us. This seems to violate the Copernican principle, the principle of cosmic mediocrity, but I will show you next time that in fact it is entirely consistent. And yes, indeed, we are mediocre. I think we've run out of time. Thank you very much. Greg, thank you very much for recording this.
Okay.